enjoyed, given that in a virtual space, virtual webinar. So I'll cover three main topics. With the first one, which will be the longer one, will be actually the failure itself, the 2021 Highway 1 failure that happened at Rat Creek in Big Sur, California, an area that is actually known for lots of landslides, a lot of things happening in that area, and so it's not a huge surprise, but it's interesting still to learn exactly what happened here, and I think there will be some very interesting details that you may find exciting. The second part of the presentation will be trying to understand why the failure happened at Rat Creek, as opposed to the many kilometer-long stretch of this highway, which has, from the broad perspective, very many similarities to Rat Creek. And so being able to understand why the failure happened there exactly as opposed to somewhere else is an important resiliency question that I think as geotechnical engineers we ought to address. And the third one will be a remote sensing, very briefly, remote sensing inspection of Highway 1 and how the remote sensing could be used to really monitor what's going on in a more scalable manner, because right now it's happening very manually and it's cumbersome and difficult in some cases. Before I start, I would like to acknowledge the Embankments, Dams and Slopes Technical Committee of the ASCE Geo-Institute. When this failure happened, the chair of the committee, Tim Stark, contacted me saying, do you want to be involved in this? And given that it fit many of my interests on the things that I was doing, I was glad to co-lead this deployment. And the goal was to really collect perishable data, really the data that about what really happened there before it disappears. But we took this, as you will see, a few steps further. But definitely, the reconnaissance part was something we started with the EDS committee, and there is actually going to be an ASCE report on a publication, geotechnical special publication, published on that really soon. There were a number of colleagues that contributed in this effort, and I have them all listed here. They all helped tremendously. I definitely want to point out Parker and Giroux, who are two PhD students who helped a lot in this work, and some of the specific things I will show you today, as well as Ryan Turner from Caltrans, who was extremely insightful. So the Rat Creek failure is shown here on the map. This is California, and this is Highway 1 failure. You can see Santa Cruz at the top. Further down the south will be Santa Barbara, and so Rat Creek is located somewhere in between Monterey and San Luis Obispo. And there are a number of creeks that are happening here in Big Sur that are of different sizes, like Rat Creek, and we'll talk about those later also. So let's start with what happened. Maybe you heard it on the news because it was definitely in a number of media channels. But basically on January 27, 28 of 2021, there was a major atmospheric river, like similar to the one that you had in Canada. Well, I don't know how similar, but atmospheric river. Both of them were atmospheric rivers, and that ended up dumping significant precipitation in the area of interest, the Big Sur area in general. And in Rat Creek specifically, a debris flow was triggered, and it reached the highway embankment, was triggered further upstream, but it reached the highway embankment. You can see it here, you'll see a better picture of it soon. Reached the highway embankment, and it essentially overtopped it, and the water kept flowing on top of the embankment and basically washed it out. Now, the first time I saw this picture, I thought it was actually a classic, almost wedge. I teach rock mechanics here at Cal. I thought, oh, that's going to be a wedge failure. That's what it looked like to me. But it turns out that it was really overtopping and erosion of the embankment. And we know that because there were locals that recorded that. And so basically, no videos, but we have photos. This is in January 28th in the morning, and we can see basically water going above the roadway to the right, which is the ocean. And you can see here it's washing out a portion of the embankment, and this lasted for a while. And basically in January 28th in the afternoon, a portion of the embankment is still there, but you can see a portion has already collapsed. So this is really what happened, but it's important to understand why, and so that maybe we can prepare and mitigate this type of effects. Sorry, I have this. I wanted to point out. I pointed out with my mouse. Now, this is a better view of the entire failure. It was kind of a big failure. I will talk about dimensions soon. The consequences of that were basically Highway 1 was completely intercepted and not operational at that location for about 85 days, which is basically 3 months, which frankly is a short period of time. Caltrans fixed this really, really quickly. They got lots of kudos from the governor on doing that. And I think, yeah, it's kind of impressive, but still, this repair cost $11 million, which is a significant amount of funds. And you can see in the back, we'll come back to that a few times, but you can see a lot of wood debris that came all the way to the embankment. There was available data from lidar data in this area from 2016. So we had a DEM, a digital terrain model, and digital surface model. We care about the digital terrain model here. From before the failure, maybe like 5 years before the failure. And then as soon as this failure happened, Caltrans deployed their drones and created another surface for the failure. And what we did is take the difference between the two surfaces, one created with a UAV with structure from motion from optical data, and the other surface with a lidar, and calculate the volume of this lost material. And you can see there is an elevation loss at its thickest position, where it's dark blue, of about 50 feet. Basically 50 feet of elevation was lost at that point, and around that there was less elevation loss. In total, we have about 18,000 cubic meters that failed. Now, to understand that failure a bit better, is important to go a bit back. In 1985, in exactly Rat Creek area, there was a wildfire, the Gorda wildfire, and that burned a number of trees in the forest area. And at the following winter, a debris flow was occurred at that location, and brought significant debris to the degree that it buried the existing CMP culvert, which was a 66-inch diameter culvert, buried it. And at that time, Caltrans, which is something they have to do, instead of removing all of that material, which was a lot of material in an environmentally sensitive area, what they decided to do is install a 36-inch diameter vertical riser, like a pipe. You can see it here on the right, that finds the pre-existing culvert at depth and allows for water to go through, future water, surface water, to go through and meet the culvert at depth, and drained that area behind the roadway that way. So this happened in 1985, and the consequence of that, of course, was a relative reduction in capacity of how much water can be passed through below the roadway efficiently. Now, this is a picture of the riser that was taken by a local just a couple of months before the 2021 failure. It was maintained, it is clear, it wasn't clogged, so I would say a pretty good shape. The area is vegetated, but really you can see that it's very accessible. Has the capacity to guide water out. Now, in August 18, 2020, so basically about 6 months or so, maybe less, 6 months, 5 months before the failure itself, there was a major wildfire that was also in the news, the Nolan wildfire. And the area affected by the Nolan wildfire was huge. It was 500 square kilometers were burned. And you can see it here, it's shown with different colors, basically the footprint of the wildfire. And Rat Creek is within that area. It's shown here. It's on the west side of this whole area. And you may know that USGS, at least in the States, when there is a wildfire affected area, they have a model by which they for awareness purposes, they predict the probability of a debris flow to be triggered. This has to be conditioned, so it's a probability of a debris flow that will be triggered by a 15-minute rainfall of about an inch, of 24 millimeters per hour, 1 inch per hour. And you can see Rat Creek had a relatively high probability. There is nothing special about these 15 minutes of rainfall in intensity of 24 millimeters. In fact, they do generate maps for other scenarios, but this is the most classic scenario that they use based on experience. And so you can see it has a kind of a 60 to 80%, Rat Creek specifically, 60 to 80% probability of debris flow. And then we came to January 27, where there was an atmospheric river that really resulted in a significant precipitation in that area, in that broader area. And so we looked at that precipitation because it was important for us to understand. We had two approaches to look at it. The classic one is to look at weather stations that are in the vicinity of the area of interest. And so these are the stations shown here. The closest one was Highland Peak, and it's about maybe 10 kilometers or so away from Rat Creek. And overall, that's not too far and similar environment. And so that station recorded about 300 millimeters, 30 centimeters of rain in these 2 days. We had a completely separate approach for precipitation. That is part of a lot of the work that we're doing also with NASA, and that is the iMerge precipitation estimate, which is basically as part of GPM, the Global Precipitation Model that NASA has developed, that allows you to estimate the precipitation using microwave technology from satellites. And that model has been calibrated in other areas against weather stations, but not in this case. In any case, if you go to the iMerge data, which is fully open access and available, you will get an estimate from that technique of about 292 millimeters, which is close enough. I would say those are very, very close. But it's good to have that, and because now we have an estimate exactly at Rat Creek, and it's very similar to Highland Park Peak. So overall we feel we have a good understanding of what the precipitation was. One of the things that I like about iMerge precipitation data that I think is something to consider for your work also, it doesn't only provide you estimates of previous precipitation, but it has a prediction with some uncertainty and error, of course. They never get it exactly right, but for the next 3 days. And then so for the next 3 days, you have a rough estimate of how much water is coming in. And they provide that for the entire planet to the degree that they can. And there is some limits about how far north and how about south you can map that. But I think it's good to think about that in terms of preparedness. Here's a little bit more the details, a bit secondary, but I think this is the time history of precipitation. This is cumulative of the iMerge precipitation estimate and the Highland it's called Park here, I believe it's Peak, and so we'll need to fix that, Highland Peak station. And so you can see they're very, very close. There is a little bit of a difference about when the peak occurred exactly in that area. So once the station, the physical station, weather station, indicates that arrived a bit earlier, but that was also 10 kilometers away from the exact Rat Creek location. So I think overall the two techniques are result in similar precipitation estimates of about 300 millimeters in these 2 days, which is roughly speaking a quarter of the precipitation that this area receives in per year. And in some drier years, it could be as the 300 millimeters may represent half of the precipitation of the year. In any case, it's significant precipitation that happened. So going back to this a little bit more of a background also, but now we worked with Caltrans, we were able to deploy there. We were allowed to access the site, not immediately, but I believe it was 3 weeks after the after the construction, after the event happened and construction was already underway. And you can see in this view the debris that came down and piled behind the roadway. In fact, it is at a higher elevation than the roadway, although before, as I will show you later, there was a significant elevation difference, and there was a storage area for water to accumulate and, of course, to be guided out. So what we did is try to trace where this debris flow came from, and I'm going to get you through this tour. So here at the bottom is the highway. This is the impacted infrastructure, and then we started working all the way until we find the beginning of the debris flow. So some pictures from that reconnaissance. You know, you can see just near the end of where the debris stopped. You can still see significant scour of about 2 meters. This is the original elevation. This is part of the team that worked on, that deployed. And you can see there is excavation of, not excavation, but a scour of 2 meters, all the way down to what was bedrock there, which is a Franciscan broken formation that is in that location. A little bit higher, you can still see about 2 meters of scour. It varies depending on topography, but here you can see about 1.9 meters. What I want to point out is, although this is a material that was scoured, clearly lower elevation of the ground surface compared to before, there is still about 3.6 meters of what we think was water submergence, I will call it, water reaching that level. I'll explain that. This is different than the additional height, which was at least 2 or 3 meters. It varied their location of splashing, water splashing, and really getting the tree trunks muddy. So we have significant amount of water coming down in this area. We do know that this was at least the elevation of water height from the marks on the trees. In fact, this tree here is fallen down, and you can see that at that location, as well as the trees that are standing, this tree was not just splashed. This tree, if you were there, you will see it even better, but there was definitely soaked underwater, and there was mud that was placed throughout this trunk. And so that's how we assessed that there was water there at some point, at least that height and a bit higher. And then beyond that, there was a splash height. And this just is as an evidence of really how significant that event was when it happened. You definitely did not want to be there. This is a little bit further upstream, and one of our colleagues, Oz Kozachi, was there, and he liked that spot because he could see significant exposure because of this scour, which you can see in that case is easily more than 3 meters, and he did a geologic characterization of the sediments. And so he took this exposure and started looking at the various sediments, not geologic units, but sediments. They're all relatively recent, and soil horizons. And a couple of things that I want to point out, which was really, really interesting. He found clear evidence of debris flows in at least 3 different locations, different elevations, which, obviously the shallower stuff are more recent and the deeper stuff are older. And so he saw a recurrence of debris flows in that area going back hundreds of years, and also found buried horizons, at least 2 of them, where there was a buried burned material. So there was some kind of a fire that burned the material, and that has been happening systematically. We did also radiocarbon dating, and just it doesn't, I don't think it's conclusive necessarily, but we did find that for the debris flows, there is about a 170-year recurrence interval of these debris flows, and which you could compare to the 36 years that we have now between the 1985 and to the 2021 debris flow. And so this could be an indication that things are more intense now, happen more often compared to the past. Although the problem with something like that is that there may have been another event that really cleared previous debris flows. And so we're seeing here at least 3, but there could have been many more. That was the sediment of those debris flows could have been cleared by a future, from a subsequent debris flow. In any case, I think it's really interesting to know and understand that this is part of an ongoing process and not something that happened for the first time. Going further upstream, we saw a lot of burned trees. Even the existing trees that you see there upstanding were charred, but luckily many of them have survived, especially at the lower areas of this creek, of this canyon, if we call it. And but they were charred. But there were many trees that were on the ground, and they were basically dead trees. And as you've seen also in the picture at the beginning, lots of them came down with debris flow, but there were lots more coming into what was now the clear channel. Here you can see a big tree that got stuck really on the turn that the topography is making. Previous ones could have gone past it if the water level was higher, but this one, the water level was probably lower and just got stuck there and stayed there. And there were lots of examples like that. I think it's important to understand because it is a significant amount of material also. You know, we tend to think of debris flows as soil, but really there is, in this case at least, huge trees, frankly, that came downstream. And I mentioned that before, but there was significant scour, and many times the scouring was clearly down to the bedrock. It would have gone lower if there wasn't more stronger bedrock down there, and that's just indicative of the energy of this debris flow. And here you can see the original ground surface was somewhere there, and this has been all cleared, and a significant height here that we have. The height was changing depending on topography, but the numbers that I have been showing you are kind of what I will call an easy average number of what we've seen there. Sometimes lower, sometimes higher. Also, it's important to consider that when these things happen, the topography is changing, and there are other landslides. Some of them we saw here. So here is I'm sitting on the bottom of the channel, and there is clearly a landslide that happened. It has nothing to do with the debris flow, but the debris flow cleared material downstream, creating an opening, and along with water, you know, this landslide was mobilized, and we know there are others that really came out as part of the debris flow. And in addition to that, all the sediments, additional sediments that come down, and that you don't really see them as a missing elevation, but really there was sediment there that is now came down. I think the reason I'm emphasizing this point is because later I will calculate roughly a volume of the debris flow by thinking of how much material was removed, and that, in my opinion, is a gross underestimate of the amount of fill that came down. And just want to bring that up. And then we reached really what was the beginning of the debris flow. It's very clear to see. It's fascinating. I've been doing reconnaissance for a number of disasters for the last 20 years, and I hadn't seen anything like what I'm going to show you here. We reached the beginning of the debris flow, and the beginning of the debris flow was at the location where the two contributing channels were meeting. That was number one, and you can see them on the left side. I'm hoping with this small animation. But what was there that was really amazing was a natural tree debris dam. And you cannot very easily see it. I will spend some time on describing this. You know, this is the type of stuff that is never as easy to explain with photos, and but hopefully you will get the point. This is there are natural trees, very big trees, large 2-meter diameter, easily, much more than that in some cases. And there were these big tree trunks that really had laid down and had really created almost continuous feature throughout this area, forming a dam. And other the tree trunks came and sediment came in and formed really a dam. And that dam definitely breached during that event. And I'm going to show you a little bit more details. And so the main breach is here, which was very, very difficult to reach and go up upstream further in that location. There is a secondary bridge through which we entered, as well as a tertiary bridge here. I'm not going to be talking about the tertiary bridge. I think it's not as important right now. But basically what I'm going to show you next is a photo of the secondary bridge, because as I said, it was the only place you could go upstream from there. You could not go from the main bridge. You could have possibly gone through the tertiary for sure. So here is a Giroux who is standing on that area, and basically the only way to go through was below these tree trunks. So basically you have to go below them, and you can see here how big these tree trunks are. And that's how we went below. There was underscour that happened in that location. We suspect after the tree trunks moved, because I'll show you that they were not they're roughly in the right position, but we think they were much better stacked and sealed before the failure. In fact, there are other places where there's one stuck on top of the other, forming this dam. Now, one way to visualize this and have actual measurements beyond measuring tapes, of course, is using a lidar or UAV structure from motion. These are tools that we use regularly in our work nowadays. Here we have Justin, who had his own lidar, and this is what you see here is a lidar, a topography of the area in plan view. And I'm just going to describe this a little bit further. The red color is higher elevation and blue color is lower elevation. Okay, and so you can see that from the high elevation to the lower elevation, there's a 16 meter, 48 feet difference in height. Okay, this is a major, 16 meters is not a small dam if this was engineered dam. You can see some of the tree trunks, not all of them. But this was basically, we estimate that the dam was looking at something like that here. And I'll show you more pictures of it. And so what you had is the formation of this dam, sediment coming behind it, water coming behind it. The dam eventually breached in that location, creating scour, and really the beginning of that debris flow that came all the way down. Okay, that's part of the story. And so that was the main bridge. And then there was a secondary bridge. I think an oblique view may be easier to see. Here is the upstream side, here's the downstream side. And again, here there's a 16 meter elevation between I wouldn't say the very top of the dam, but basically the upstream side and the downstream side, which of course that hole here was because of scour, right? As the dam breached, water came under pressure and really started washing out the material and creating the debris flow at this location. Now, I want to emphasize that throughout this point, up to this point, the debris flow was continuous. It's not like yet there were points that there was no scour. From this point, here being the deepest, there was scour throughout. And on average, as I said, 2 to 3 meters easily, in some cases higher, but always there was scour all the way to the roadway. Above that, there is, the stream beds, and there is a little bit of of course, a stream bed, but there is nothing like it. In fact, what you see here with red color that looks like a flat area, and I have some pictures to show you that, there was no other area a little bit further upstream, and definitely nothing like it downstream, where there was such a flat spot. What you're seeing here is the only place where there was this flat spot. And everything else was really in the channel, very difficult to walk through. And so when we went, as I said, we went through the secondary area from here and climbed up here, and we saw this. Oh wow! You immediately realized something different was here. And basically, what you're seeing is the upstream side of the dam. And I'm taking a picture here. You see that the tree trunks that are above the ground, although there are additional tree trunks below that ground, and we can see them on the downstream side. If you can see in this point exactly, it immediately becomes extremely narrow and significantly lower elevation, as I described before. Okay, so you're seeing here the very top of this natural dam and the sediments that accumulated behind it. Okay, here is a closer view of the bridge. This is looking from downstream, and I think that the Big Sur doesn't describe the elevation difference. As I said, it was not reasonable. I mean, you could have done it, but you could not climb from here. There was 16-meter elevation. I'm still not at the lowest part. I just tried to approach it. And this is from the downstream side looking towards the dam. The original ground elevation was there. And then here is the location of the main bridge looking from above, right? So where, if I go back to these pictures, here is the main bridge. This is the main bridge. And you can see it here, and I'm going to show you another picture. This is where, when the bridge happened, these huge tree trunks, at least two of them, broke. And I have another picture here. They broke, and you can see very easily that this piece was that piece. You can see what's missing from here. It's there, although the tree trunks are stripped, and because of course once the bridge happened, you can imagine the energy that came out of it, and of course caused the scour. And so this burst energy in the tree trunk is very indicative of really what happened here. It was not like a small failure. Definitely what the soil was washed out below it, so there's a hole here. And so once of course the failure happens, it's very difficult to know exactly the details. But another observation that I was fascinated, and maybe some of you in the field have seen stuff like that, but this is the first time I saw this. I'm sitting on one of the tree trunks. As I said, this is the one that has moved. This one is roughly in the right position. You cannot see the ones below, but there are other tree trunks below it. It's almost like this was engineered by beavers or something. But these are huge trees. On the upstream side of the tree trunk, the tree bark was stripped. So what happened probably is water and debris started gushing out at high energy and completely stripped the tree bark, something that you don't see on the downstream, which was exposed to the air, let's say, on the downstream side. And so you had this feature here of really like perfect distinct point between the stripped and the unstripped tree bark. Again, the reason I'm describing all of this is because the energy of the system must have been very, very high. This was not a small failure. It will have looked spectacular when that happened, probably very noisy. And of course, that's the energy was released, causing immediately scour at the bottom and mobilizing the debris flow all the way down. So this dam definitely played a role. We can't really know if this dam existed for a very long time, but this is our suspicion. This dam did not form during this storm. We believe these tree trunks were there for a while, and then of course additional sediment has been accumulating, and this event basically broke it. Okay. I want to go to, with that understanding we got at the beginning of the debris flow, I want to go back down and see what happened at the roadway. And where we know, of course, it was overtopped, but let's talk a little bit about the details. Now you can see again all the tree trunk. These look like a small, like almost like a mulch, but it's not mulch because you can see the size of this police officer's car. These are big trees that are just sitting there. They came down from that hole there and deposited and basically filled in the entire area. But before the failure, we luckily, again, we have the 2016 USGS lidar data, and we can use that to assess. It's been 5 years, of course, but we think it's close enough. We're really lucky to have that, and so you can see here the 3D point cloud with the vegetation. So first of all, you can see there was significant elevation difference between the top of the roadway and the ground next to it, and we call that debris or water retention area. In fact, this is where the previous, inside this vegetated area, is where the downshoot was located, the 36-inch downshoot that was located. But also because it's lidar data, we're able to see the terrain itself, and so we can actually calculate how much water or debris could fill this, is needed to fill this before it overtops the erode surface. And you can do these calculations in virtual space, and you can see it here filled in with water. Of course, it's filled in with debris, but also debris and water. And here it's the same thing, it's transparent, so you can see the surface. We like as geotechs to cut cross sections. I think we still do that, and we're going to do less of that in the future. I think everything will be looking at we need to be trained looking at things in 3D. But definitely, let's cut a cross section through here. And what I'm hoping you can see is that the roadway, this looks like a levee, but it's not. It's the roadway. It was not designed to retain water. And there's a 9-meter height difference between the top of the roadway and the base of that in that location. Okay. So what we can do is calculate the difference or the volume, the difference between this sort of 68-meter elevation surface and the ground surface. And you can see that here you see the difference between that in plan view. There is up to 11 meters of difference in the deepest spot. I showed you before 9 meters because it was not cutting through the deepest location. The cross section was cutting through here, and so you can see here 11 meters, and of course much less capacity along the perimeter. This is without considering the vegetation, so about 25,000 cubic meters of capacity, meaning that this could fill with water and sediment as much as 25,000 cubic meters, and you will not have overtopping of the road. However, it was filled with vegetation, and you can use that also to calculate volumes. It's not fair to try to calculate volumes from vegetation because that's not what we're mapping there. But in any case, it looks like, because of vegetation, you could have had half of the capacity. So, don't take these numbers for like very strictly, but roughly the capacity of that basin was reduced because of how much vegetation has grown. Now, if I go back to the debris flow that I showed you and I calculate roughly the volume, it's roughly 3,000 to 19,000. Oh, this is a very big range. It's a function of a number of things and assumptions I can describe. If you had if you had me guess, I would suggest closer to the 19,000, and that still doesn't include any tree trunks, any sediment that came from the sides that was washed out, and definitely doesn't include water. Okay. So the debris flow is smaller than the full capacity overall, possibly even smaller than the capacity with vegetation. Just the debris flow, but it's big enough to do two things. Number one is reduce the capacity, storage capacity. Number two, and most importantly, take out the downshoot, take down the water, the downshoot that will guide water from the upstream side of the roadway to the downstream, and that was really the biggest thing. So let's understand a little bit how much water came down. Again, keep in mind the numbers of 25,000 cubic meters capacity, let's say 15,000 debris flow as rough estimates. So what we did, and I want to acknowledge Parker Blantz, another PhD student at Berkeley who helped in many other aspects, but this is something that he spent additional time on. We did a hydrograph analysis of this area to just calculate what's the hydrograph. The hydrograph tells you how many cubic meters of water is coming to the point of interest, and in our case, the point of interest is the roadway. It's the place where the water was being, where the culvert was, basically, for a given precipitation. So we took the precipitation estimates that I showed you before, that is changing with time. We have that precipitation hitting that terrain, which has steeper and flatter areas, and see how long it takes for water to come from the drainage basin, even the farthest point, to the surface. That's what really the hydrograph is. So it took about 40 minutes for the farthest drop of water to come down to the basin. Okay, that's really what the hydro, and this is the result of the hydrograph. So here is for the entire event. Again, flow in cubic meters per second. This is how much water is coming per second at the location, at where the culvert is. Okay, and so that's really calculated, and you can see that the total amount of water was 700,000 cubic meters. So it was a lot of water that came down that needed to be cleared, right? Much bigger than the basin capacity of 25,000 cubic meters, or the debris, or even the debris flow, which was similar in size. So we like to describe this a little bit more. And so again, this is the hydrograph. It's a previous figure I showed you, but I have added two things here. Again, flow per cubic meters per second. And the orange line is the capacity, the nominal capacity of the 66-inch culvert that existed before the 1985 event. And that's how it was first built, and that's how much water per second it could guide. Now, as I said, we had to, when the 1985 debris flow happened, they were able to put a downshoot to that culvert, and they were not able to put as big of a downshoot, so they put a 36-inch culvert. This is the best they could do to guide the water. But of course, that immediately reduces the capacity of how much water can be guided. In any case, those are the conditions. So the conditions encountered is the gray one. You can, and the blue is from the hydrograph, how much water needs to be guided in. So up to this point here that we'll point out with my cursor, really all the water that's coming in can easily be tackled on by the 36-inch culvert, right? At this point, there is more water coming in than the culvert is able to carry. And you can see that total area here is really how much water is not able to be carried on effectively by the culvert. But then the precipitation, at least for some time, slows down. And if this really water had piled against the culvert, during that time, the culvert has still that capacity, could remove it, has a time to remove it. And then there's another big pulse that is coming, and again the capacity is exceeded, but not for too long. And again, the culvert could recover. All right. So this will have stretched a little bit the 36-inch culvert. But really what happened, and we know that from the testimonies of people who were there, already by this point, we don't have earlier information, but this is 8 o'clock in the morning, and we had the testimony telling us there is already debris flow, the culvert is gone, and the water is rising. So it could have happened earlier, I suspect sometime during this peak, or we don't really know, but definitely by that time, the debris flow had already came and destroyed the downshoot, and the culvert basically no longer had any capacity. Well, it may have had some, but practically none. It was filled with soil, not buried with debris, right? So, at the point 2 here, although you can see that the water, that we had an opportunity to take the water out. I mean, it's still raining. Nobody can be there. It's not safe, of course, right? So this is the one vent. You're just waiting to see what happens. But at number 2 time, the water is rising, and really the water is still below the road elevation. So even at this point, the road had not been overtopped. The next day, this is the next day in the morning, the embankment is now a highway. I don't want to call it embankment. It's a roadway embankment. It's not an embankment that was supposed to retain water or debris. It is overtopped, but the embankment, the roadway is still there for the most part, the majority of it. And it is really in later in the afternoon of the 28th that the majority of the pavement has washed out, and of course you've seen the final outcome. So this is the story, and I hope you found it interesting. When I first got involved, I had a colleague, and he told me, "Oh yeah, of course, this stuff always happens in that area, And so I said, "Okay, maybe it's not very interesting to investigate." But I have never been surprised. Not surprised. I have never. Every time you go in the field, if you go, you always find some really fascinating aspects of the failure, and I think this one had lots of them. So I would like to conclude this the first part of the presentation. Again, I don't want to scare you. This is the biggest part about really what happened in this failure. And so we had a combination of things that took out really this roadway. Each of them on their own probably will not have taken it out, but it's a combination of hazards, a combination of events that took it out. We had a combination of a wildfire followed by an atmospheric river that caused a lot of precipitation, an existing debris tree dam that gave a lot of energy and triggered the debris flow, all of which happened basically upstream from the roadway. All of these events were not on the roadway, were upstream. And then, of course, caused the roadway failure. The wildfire provided the material, soil, and tree trunks that was ready to go. The precipitation was significant and carried that stuff. It breached the dam that was pre-existing as far as we can tell. It doesn't really matter even if the dam formed and filled during that event. But as if you were there, I think you feel that this was there for a while. But the breach of that dam mobilized, triggered, worsened, and must have triggered because the debris flow started at that point. So it's not likely that the debris flow was starting elsewhere and then this made it worse. This is where, with the energy that came from the dam breach, this debris flow was triggered. And the debris flow, of course, brought a lot of sediment and water in it, but basically took out the culvert, basically eliminating the defense of that roadway from the additional precipitation. And I think that's and I think it's important to understand that we have the confluence of these things coming in. Each of them on their own could not be problematic necessarily, but all of them together caused that major failure. This also points to the need to assess areas beyond the immediate transportation corridor. The transportation corridor in this case, in many cases, is part of a broader system and maybe in the receiving end. And so just looking at your corridor may not be enough from a resiliency. Well, in this case, was clearly not enough from a resiliency perspective. I think Caltrans was taking care of the area. It's not like it was not taken care of from a perspective of having some capacity for surface water adjacent to the roadway. So we made some recommendations that kind of were obvious. In this, debris collection basins need to be cleaned out systematically. It's better if there is not a lot of vegetation there. Maintaining flow capacity of culverts is very, very important. Installing overflow emergency culverts can be very, very useful, so that if the big one is gone, there is a little bit of an additional defense. In this case, if this existed, there is we can do the calculations, but there is a chance that they could have actually protected the roadway. And finally, developing a risk assessment framework for identifying which basins are of concern. Not all of the basins are the same is important. As I said, Caltrans, I don't think they expected they waited for our recommendations. They worked on that direction. I want to show you with pictures what they have done here. You have a 3.1 meter main culvert here now. That is huge compared to what we had before. If you think about the 36-inch or even the 64-inch, 65-inch culvert, this is higher capacity. There is a secondary culvert at the higher elevation. If that was to be damaged or buried, there is still a significant capacity here. And even if that was to be filled with debris, there are also at the very top two 24 inches, 0.6 meters emergency culverts that should help and hopefully save the roadway if that happens again. In addition to that, a row of solder steel piles were installed at a distance from the culverts. And the idea is that big stuff only, like tree trunks, I showed you how big the tree trunks are, will come and stop there and really not clog the downstream area. And then, of course, you will have to come here and clear that area, but it will remain upstream from where your culverts are. And so with that, this concludes the first part of the presentation. I want to just very briefly touch on two more topics, keeping track of time also. I think I'm doing okay. Just looking here. How much time has it been? It's been yeah. All right, I think we should be okay. So I'm always answering, trying to answer that question. I feel as a geotechnical engineer, we have the principles, we have the background. We can easily go back to any of these places and where there is a failure of a landslide or something and say, oh, I can tell you why this landslide happened. I'll do a borehole, I'll do an investigation, put material properties, run stability analysis, and show you the factor of safety is 1 or less, and of course it failed. And philosophically, as part of my career path, I don't think this helps us with resiliency when after the fact we're able to be smart about it and say, oh yeah, I can tell you why it failed. So if we want really to help our resiliency of our communities, we need to be able to answer why there, over a stretch of many tens of kilometers of a Highway 1, why it happened there. And if we're able to answer that question, then we can start thinking of schemes by which we will be able to prepare for it and anticipate failures, as opposed to react after there's a damage and trying to fix it. And I think that's the challenge, given climate change, everything that's happening here in this world. This is the challenge that we need to face on as geotechnical engineers. And there's a lot of tools we have right now. So we'd like to talk a little bit about this. And that, of course, involves a Highway 1 system performance assessment, again, focused on that specific event. We're not doing a system performance long-term. We're just learning from that January event. So the way we did it is leverage the work that Caltrans has done, that they're doing all the time, and looking at the various basins. And they gave us the 44 basins. So Rat Creek is here. All this discussion has been focused on Rat Creek here. And you can see, before I go any further, that there are a couple of more big basins, but then it's very big. So I want you to see that visually here. I'll point that later, right? And so we used the Caltrans inspection data. They had photos along Highway 1, and we collected some of our own data, although not as extensive and that far south as they did, and look at the system. And what we did is classify the conditions. So in 5 classes, class 0 is no damage, like really nothing happened. Class 1 is minor damage, really meaning that there is stuff that came on the side, debris, sediments, but it's very small. Really, the highway is not affected by it. Someone should eventually pass and clear it, but the highway is full capacity. For practical purposes, nothing happened. Class 2, you start having moderate damage. And so that means that the road is partially obstructed. It's still operational. There is 1 or 2 lanes. So, I mean, this is a 2-lane highway for the most part. So there's at least 1 lane. Cars can go by. But there is time-sensitive cleanup work to make it fully operational again. Class 3 is moderate to severe. The road is partially closed. In a way that really you need to go there and in a big way and spend time, and of course time is money also, to fix it. In some cases the road may have some debris that you can still drive on top of it, but it's not super safe. And definitely, systems around it, like surface water drainage systems, are so damaged that you need to come and clear it up. So maybe there's a debris flow that came and reached the highway, stopped on the side, nothing else happened, the highway is there, but really you cannot leave that stuff there. And that costs money to fix. And 4 will be severe, like complete damage of basically the roadway not interrupting. And we have, of course, Rat Creek belongs in that category. So I hope this system is useful. And so we did this for all the basins. And before I go to further detail, I want to show you, because this is what I like in my research, always to be fundamental, but also very practical, and really see how it affects the bottom line, how it affects the owner, in this case Caltrans. And so here, here's the damage ranking system as a function of cost estimates. And you can see that when you have 0, 1, 2, you have costs that are, $100,000, which, it's not welcome to lose that money, but at least it's more regular. But then as you start going to damage ranking 3, the costs pick up, and we have 2 basins in damage class 4, and Rat Creek is off the scale here. The scale goes to $1 million, and the Rat Creek costs $11 million. So, you know, the point will be off the chart. I don't even show you this figure because all of that stuff looks like it's zero, okay? And so, I mean, again, our damage scheme had nothing to do with the cost. In fact, we developed it before looking at the cost, but just on the visual inspections and all the discussions. But it's good to see something like that. And there's far fewer points here because that's the level of discretization that Caltrans is able to provide us in terms of cost, you know, meaning that there are many basins that had very minor things to zero, and they didn't really cost money, or if they cost, they didn't track it separately. And so we have lots of points down here. I'm going to show you more points for the rest. Let's go to the more interesting things. Here I'm plotting along this entire stretch of the highway a basin area size and damage ranking. And you can see here that Rat Creek basically is the 3rd largest basin. I showed you that before. It's really the 3rd. In fact, when we started looking at this, we thought it was the largest. And we said, oh, it's the largest basin. That's why it failed. But the largest basin area means that more water, total volume of water will come. If there's a certain precipitation amount of precipitation, you multiply that amount of precipitation by the basin area that receives it, and you have cubic meters, which is basically the water you have to handle. So it was the 3rd biggest, it's not the largest. But let's look at the other 2. The first one is the Mill Creek side, which is actually not really a culvert. It has nothing to do. This was actually the site of a previous failure. As far as I know, though, I haven't looked into that. And they decided to, instead of having a roadway anymore, they built a bridge. And so, although it's very, very big, there was minor damage on the sides, really, but really nothing happened because, in reality, and this is satellite imagery, there was a major debris flow that happened here. And I have seen another picture that unfortunately I don't have permission to show, but there was a huge debris flow. This is the bridge. Maybe you can see here with the shade, the bridge. This is the bridge. I should have annotated it. This is before the event, and this is after. And there was a major debris flow that came and moved around the piers of that bridge, and the bridge remained intact and the road remained safe. So that's really why this was there. The second one is the McQuay Creek that has really a huge culvert. That culvert here, you can see the size, is really a reinforced concrete box. It's no longer a culvert the way we've been talking about this diameter. It's a huge box, 84 inches by 120 inches. And so, of course, we realize when we see this point, it's not just about how big your basin area, obviously. It is also about what kind of surface water management system you've put, right? And so what we are going to show you next is I'm going to have all these points. I'm going to have the basin area and then divide it by the nominal culvert sizes, all right? And so I'll do that now here. And let me explain here. This is basin area divided by the cross-sectional area of the culverts. No longer the bridge. I don't think it's fair to put the bridge here. But the McQuay Creek was the point before, now plots there. It's had some damage, so not that much, but really, although it was a very big basin area, it also had significant culvert capacity, and it plots there. Going back to Rat Creek, this is where Rat Creek was in before 1985 with a 66-inch diameter culvert, right? And from 1985, really, when the downshoot was put, the culvert size was reduced to 35 inches, right? And so you can see now when you calculate that, how this point really becomes here. And you can, I think in my opinion, this explains, along with everything else that we discussed, that this type of calculation showed you immediately that Rat Creek was likely to be the most susceptible to an event like that. So if this calculation is done in the future for all the areas, you could start saying, hey guys, I think we need to be careful. Now, I think the design engineers, when they did that, they knew that. That's why they put a high capacity here, but there was a decision that had to be made at some point in 1985 about putting a smaller culvert that was deemed acceptable, and it had been from 1985 to 2021. It worked well, as far as I know, but that event took it out. And I think this is the conclusion, that second section where I'm talking about why I think Rat Creek failed, and I'm hoping I'm convincing you about that. The last and even smaller part of this presentation is talking about system-wide inspection, and I'm using here the January 20, I have my dates wrong here, 27 to the 29th precipitation event. On the 28th is when the failure is. The event, the precipitation started on the 27th. The idea is, can we have in a system like that, in a roadway that is so long, is there a way by which we can inspect things in a more scalable manner? Because frankly, it's very resource consuming to operate facilities like that. Some of you may work with levees, may work with tunnels. You know that these long features, it's very difficult to keep track of. So here's a picture from world view imagery, and this is before and this is after. Obviously, you can very easily see the after impact. But one thing I will point, this is a 0.5 meter high resolution satellite imagery. I think looks great. The problem with this is that it's not often enough. So really, we had a before image from a year before the event, roughly speaking, and the after image was in May. The event happened in January. This is in May, but there was no other images. Now, Worldview is working on Maxar is a company, the same company now. Is, you've seen some of the footage from the Ukraine war. They have similar things there, but basically they're trying to have more satellites of this type of resolution for the future. But that will not work with us because, you know, having one photo of high resolution per year, that's not good enough, I think. There is an alternative such as planet imagery. Now, planet imagery is not of the same resolution. It's 3 meters resolution as opposed to 0.3 meters to 0.5 meters for worldview. But the big difference with planet imagery is that it's available daily. If you're signed up the way we are, you can go and basically have a picture of any place in the planet, assuming that there is no cloud coverage, anytime, every day, sometimes more than once per day. Now, already by seeing this picture, you can see this is the whole section of the roadway that we're interested. It's more difficult to view things optically, right? But the idea is, can we use some kind of an automatic change detection? Because nobody really will sit down with a satellite image, start zooming in and looking for debris. And so our focus was on a scalable, simple, scalable approach to maybe detect things, at least as a screening tool. I'm not considering that a definitive tool, but as a screening tool. So one concept that maybe you have seen, those of you who work with this remote sensing data, is the NDVI index. And the NDVI index looks at the red component of the visible part. So you all know that the visible part of the spectrum, what our eyes can see, is the red, green, blue, RGB, right? And uses the red component of that, but then goes to lower wavelengths, longer wavelengths, lower frequencies of the electromagnetic spectrum into the infrared, and specifically in the near infrared, and looks there, okay? And you just have to have a sensor that does that, which many of the satellites do. And the NDVI is the difference between the near infrared spectrum and the red, minus red, and then divided by the sum of the two. And what that does is it has been shown extensively. There's so many papers on this, also in our field nowadays, in geosciences and definitely in agriculture. You can use the NDVI. Very low NDVI values are indicative of ground, rock, sand, snow. Vegetation tends to have a bit higher values, roughly speaking, 0.2 to 0.5, roughly speaking, again, as I said. And then dense vegetation has a lot of green, right, of the spectrum. There is not a lot of a red component, tends to have higher values. And so just that already indicates that maybe we can see things. But the value for us will be not just even on these values, but the differencing. If I have imagery data to calculate NDVI before or after, or maybe the NDVI every day, I can look when things are changing. So I don't even care about the actual value. I care about the change. That's what we call differencing. And maybe I can detect things. And so, for example, this is an NDVI differencing done in 3 different basins. So this is Rat Creek and NDVI differencing. And when you see red, it means negative values. So whatever it was before, it became more negative, right? It became more negative. More negative means vegetation loss. It was greener and became more closer to red. This is oversimplification what I'm saying here, but basically it indicates loss of vegetation. Okay, and so what you can see here is basically loss of vegetation. You can see it in the Rat Creek, and these images, by the way, these are the next after the event immediately. It's not a few months later. Another basin here, you can see the red. And then this is Mill Creek, where there was a big debris flow. Of course, it was not affected because there was a bridge, but there was, you can see it actually throughout. All right. Now, so I'm hoping that you can see there is something there, right? Now, there are other places that are red. Okay, that's not the only place that is red. We are going to focus, though, what we're already interested right now is on, and you could focus on those. You could go and see why this became more negative. And see those, because there's definitely something that happened there. It could be though other reasons too. Okay, so what we did is, as a trial, is to go and just look at the range just around like 50 meters. I believe we use different lengths, but at the end we did 50 meters along the roadway only, and look at the NDVI change. And so this is nearly one of my final slides, but what I'm plotting here is negative, how much negative values of NDVI I had in that region. I have some positive change. That's not the kind of change that I expect. Vegetation is changing, and so that's a different thing. We're looking at negative values. And in places where I had rank 0, meaning nothing happened, you can see there's basically no, this is basically here cells, like think about it as a distribution, how many percentage of cells being negative here. And you can see there are, and how much negative. So this is the NDVI value difference. Like it starts with 0 and becomes more negative. So you can see here some data, very little and small negative values, close to 0. You go to rank 1, and you have, of course, a high value here because there's lots of data that's a little bit of negative, and then it goes further, right? In rank 2, again, we don't have the same amount of data everywhere. What I'm hoping you can see is that I have a wider spectrum, more cells that are negative and for a bigger length. Although the blue seems busier, it drops off quickly in terms of distribution, while the green one remains negative and to a lower values in general. Rank 3, same thing, wider spectrum, and even negative value here of about minus 0.09. And rank 4, we only had really Rat Creek at that category, but you can see Rat Creek is very wide, very negative for a wide range of values for lots of different cells, and reaches values of minus 0.11 almost. So as damage increases, we observed lower NDVI values and wider range of lower values. If I were to schematically make an approach out of this will be rank 0, rank 1, rank 2, rank 3, and rank 4. Now, again, I don't want you, this is more like a framework. I'm not saying this is what you should be using by any means. This is very specific for the area that we studied, leveraging only the January 27th event, right? You could start playing with this concept, not just for that event, but for other events, and see if this approach works in general. I suspect it will. The values themselves may change, but the concept should make sense. And so you could have an approach by which you scan on a daily basis, every month, every 2 months. You scan that area and you're looking for change, as opposed to sending a person traveling this many kilometers and maybe they will miss something also. And that is the last conclusions on this part of the presentation. I believe we need to start thinking at the system level as opposed to the component. We think about the highway as opposed to the bridge, or the bridge or a specific place of the roadway. We think about the entire levee system. We think about landslides along the entire length of one, as opposed to just one landslide. This will help us identify the weakest links, in this case, in the transportation system. With that approach, the very simple stuff that I showed you, I think Rat Creek was the third largest drainage basin, one of the biggest ones. It was the most critical drainage basin considering the capacity of the culverts, and had also a history of debris flow. So when you start thinking that way, I'm definitely not blaming Caltrans for not thinking that way. Maybe they are thinking and didn't have to get to it. I believe there was a plan to fix that, but you know how everything, you're all engineers, know how the budgets work. But this type of thinking, if someone starts doing this type of thinking, may come up with different priorities. And finally, autonomous remote sensing methodologies can be used on a continuous basis, possibly, and be really efficient. I'm not saying that you won't have to go there. Obviously, I'm a geotechnical engineer. I know what it means to be on the ground. But you can have that fully autonomously, scanning, identifying you hotspots, and then if you're busy, okay, don't go and see other places where I don't expect that you will see anything. Go to these 1, 2, 3 places which I think are the worst. And if those look good, you're done. If those look problematic, then you go and look at the next ones also. So a methodology like that, the way I presented it, will include, for example, to use satellite imagery as input. And there is a lot of renovation happening with the satellite imagery. If you have any concerns about the quality of data from satellites, I can tell you the technology is improving tremendously. Private funds, we will be able to see better and more often. You already know that because some of you have been using Google Earth for the last 20 years. There's a big change compared to that time. Then you have satellite imagery as input. You apply a trained algorithm that will be an algorithm like the one that I showed you that has some thresholds by which you say this could be a problem. Obviously, an algorithm like that should be trained beyond that specific event that I showed you here. Detect significant changes and focus assessments there. And then, of course, confirm on the ground in these specific areas and act if you have to act. And obviously, monitoring on its own is useless unless you have an approach for acting on the data you're collecting. And with that, I hope I didn't go too much overwhelmed. Length, I think it was about an hour, I hope. And I want to thank you for your interest and for being here, and acknowledge all my the collaborators in this approach, as well as the students who helped more on that, and partial funding from NASA on this type of work. And with that,